seat right there if you want to. Science girl, how are ya? So am I.
Oh, this is supposed to have a link built into it. It's not working. Dang it.
Is it just a link in general, or can we get to the internet?
No, this graphic is supposed to be a hyperlink.
Oh.
So I better do this the old-fashioned way.
Which element is that on your shirt?
I have no idea.
Hydrogen and lithium? There's supposed to be three on there. Hydrogen and lithium, yeah.
Not sure.
Okay. Yep.
Not sure what comes up for you.
Lithium, beryllium, carbon.
Lithium?
Huh?
Lithium?
Yeah. Hydrogen, helium, lithium, beryllium. And then, what is it? I can always get mixed up with cobalt. And then,
Well, we
nitrogen
can go up
oxide.
to carbon because that's when you start losing the energy.
Yep, that'll suck it up. Yeah, are you the property of Chiefs football or is it the shirts?
It's probably a shirt.
Because I was going to say if it's you, could we have some money?
I wish.
Yeah, ain't that the truth? Yeah, I've got a lot of different sports team shirts and stuff. First time in my life I bought one with one player's name on it, number 87. He is just a big kid.
Oh, he is.
Yeah. Reminds me a little bit, hey Dave, it reminds me a little bit of my late husband. He was kind of like that. You have to sign in even though we know who you are. Put your name on there, that's all you have to do. He looks so annoying.
Hi.
Oh. Hey, Sam. I've got to move up and get people.
Just got out of an art class.
An art class,
Figure drawing.
figure drawing.
Nude figure drawing.
Huh?
Nude figure drawing. I watched it.
Did you have models?
Yeah, we got a nude model. But we had to put a skeleton in the model. So we had a skeleton next to the model, so we drew the model, and then we put the skeleton. Then
Yeah,
we had a skeleton
okay.
next to the model.
Yeah.
Interesting.
Yes, if your tibia is longer than your femur, you got a problem. Although, my 9-year-old grandson was playing football at the reception, and kind of fell down and tackled, broke his femur. Mid-ship.
That's crazy.
I know, he was in a walker, he's walking with a
Put a
rod pins,
rod,
yeah. Yeah, it was a transverse mid-shaft, but was displaced a little too,
Didn't
so,
see the email until I got home.
yeah.
that's a
Just a
big
little bit.
bone, and that's a big strong bone.
I know.
Well,
Strong
should
bone in the
we,
body.
should we give people a few more minutes?
Quite an impact to break
He,
it.
well, he said that a couple
Yeah,
of kids
just
in there playing
reminding
football, they went
them
down on
and,
the grass, and he said he got his
talked
foot
about a
caught
few
in the foot.
things,
So I thought, well, maybe it was a
that I
spinal
didn't
fracture,
know.
but it wasn't.
But yeah, the ball field.
Yeah, and it was a jagged break too. I wonder if somebody
Football
did
will be
fall
ready
on
for
it or
fall and
something. But, yeah, and earlier this year he fell off.
talked
No, he
about
just fell
the,
down playing soccer or
cable,
so. And he broke
or
his
internet
clavicle.
cable.
It
So-
doesn't have to do
Talked
this.
about.
Well, I think what it is, when he,
Yeah.
when he was 4, he broke his clavicle, they're gonna send him up
That'll
to
be
Children's
towards the
Mercy
end
and
of
have a
everything.
pediatric,
If they do it, like I said,
concerns with knee.
it's a little nuisance, but we would
To see
rather
if
have a
his
gate.
bone
than have,
formation is right.
right
You know, he's got
now.
some Huh?
Endocrinologist?
Yes, that's the one, yeah. Because you just don't break a bone like that. Nothing.
There are conditions.
Yes, there are.
that,
I know.
of handicap.
One thing I do know.
But even certain vitamin deficiencies too.
Uh-huh.
So
Yeah, and the kids,
low
no calcium or D.
yeah, low D, because I'm looking cosmetics.
Yeah, Well, and he doesn't have any, bones aren't bowed or anything, you just don't
Hey,
break a femur. Was just getting your, yeah. Like I said, I thought maybe it was a spinal fracture and twisted, you know, that could, but no. It was very jagged, mid-shaft, straight across. And
It sounds
displaced.
unusual because the bones are so strong.
I know it, that's why they're worried.
all right, why don't we go ahead and get started?
That'd be great.
First of all, I'd like to welcome everybody. Looks like we have some new faces, so welcome particularly. Perhaps since we do have some new folks, maybe we should go around the table and introduce ourselves. My name is Doug Gooden. I'm the president of NECAL.
Sanford Pomerantz, I'm psychiatrist.
Which we need in
We have our own
Yes.
psychiatrist.
Yes, we do, especially at like 2 in the morning. And I'm Janelle Burgard. Kids call me the Star Lady. And I do the education stuff. And sometimes I get to look up in the sky.
I'm Parker Lessick and happily retired.
Mark Clark. I recently moved to Topeka, so I'm a little bit closer, and so this is my first time here. Just interested in the group, and I've always kind of looked up. I'm a landscape photographer as a hobby. Your stuff is to pay for my hobby.
Yes, yeah, we know how that works. You have to sign in because you were late.
Also, while you're there, give us your name and.
Yeah, do that.
There you go.
Yeah. He's a lefty, so you know how that works. I know it.
You can just put your name down, so you don't have to put your.
Yeah, put the rest of it down.
Well, I'm Dean Romero. I'm on the board of
Yeah,
NECAL.
come on. And you are?
Tony Castaneda.
Yep.
Everybody.
Mhm.
Sorry, I'm late.
And?
Lynn Press, retired from Washburn.
Mhm.
Dave Cromer, NECAL treasurer, and I operate the big scope out at Farpoint on asteroid work, along with Gary.
And I'm Gary Hugg, I'm the dinosaur of the group.
By very little.
I'm Trace, longtime lurker, first time attendee.
I think, what's your last name? Is it Hutchins?
Gillespie.
Well, that wasn't even close. I remember the name Trace.
It was the next door letter.
Well, yeah, this is true, in the alphabet, yes. Well, glad to have you here.
Thank you.
And-
Takara.
What?
I'm Takara.
Takara? And why are you here?
Because when I grow up, I want to work at NASA.
Did you hear that? When she grows up, she wants to work at NASA.
Wow, that's awesome.
Cool! Girl after my own heart. All right.
Russell Valentine.
He's
All right.
our resident burglar.
Yeah. Well, again, welcome everybody. Also, welcome to those who are attending virtually. Let's see. As far as announcements and stuff goes, anybody have any announcements they want to pass along?
We mentioned this already in an email, but between Farpoint's observatory and my personal observatory, we've now reached over 25,000 observations sent to the Minor Planet Center, so.
Well, that's not counting the ones we turned in that weren't needed.
Yeah,
It's
well.
not count, yeah, there's a
So
lot
there's
more
more
that
than
ended up not being
Mhm.
yeah,
Yeah.
part of that, but 25,000, you know,
Let's see. I tried to get in touch with Mike the other day, and I have not heard back anything from him. Has he
he's
kind
still
of?
alive,
Is he?
last I heard.
Well, I'm going to follow up with Bharat to see if will be interested in giving the presentation next month. So we'll see if we can get him in here, which again I'm very much looking forward to. Bharat Ratra is a faculty member at K-State and a cosmologist. He's a professional, and I'm sure he will give an absolutely fascinating talk. But anyway, as far as announcements go, there's a new schedule out. Of course, you know about this meeting because you're here. The next public night is a combination public and member night, and that'll be on March the 18th. Is that what day of the week is that? Is that Friday?
I think it's a Wednesday.
Is it a Wednesday?
No, can't be the Wednesday.
No,
It's gotta be a
Saturday.
Saturday.
A Saturday?
Saturday, yeah.
Okay.
Mhm.
Let's see. Next general meeting is exactly a month, March 23rd. And then as we start getting into the warmer time of the year, we'll start getting more public nights. So we'll cross our fingers that we actually have some clear skies to do these on. But anyway, for those of you that are kind of new, these are opportunities to go out and visit Farpoint Observatory and look through the telescopes. And for those of you who do become members or already are members, the members' nights are nights that are kind of reserved for members to go out and pursue whatever interests you. So good chance. I think the first time I ever went out to Farpoint was during a members' night. And it was a lot of fun. So
I'm going to throw one in too, just since we've got new people here. One of the things we do at Farpoint is sometimes we'll have groups come out, especially classrooms. And we had a classroom scheduled to go out tomorrow, but it's already been canceled. The teacher contacted me, so I went ahead and
Okay.
canceled it.
Okay.
Between the sky cover and the bitter temperatures, we're going to reschedule that for early March, I think.
okay, yeah.
So if you were planning on
Is
staffing
it
that.
March 11th, wasn't it?
10th and 11th, Friday, Saturday, yeah, they want to do it then, so.
Well,
But that is one thing we do, and one of us goes out and talks to kids in their classroom and stuff like that.
that sounds good. Yeah, tomorrow night's not looking very promising
Yeah.
anyway. So
No.
okay. Any other announcements or anything anyone needs to know? Okay, well, as I promised last time, I was not going to talk about news because, we already covered that during the week. But I noticed this one the other day, and I just had to kind of bring this up
Oh, yeah.
because, as Gary and Dave mentioned, one of the things that's, and for those of you perhaps that are new or may not know this, one of the things that the club does is basically follow up observations on near-Earth crossing asteroids, which, as you probably know, can be hazardous. Anybody who's ever traveled to Arizona and seen that big hole in the ground there knows that that big hole in the ground came from a not such a very large rock hitting the ground, and if anything bigger than that hit, it could be a really serious situation. So there's quite a bit of interest right now in tracking these things, and I think it's been about 10 years ago now since NASA sort of mandated, or the Congress mandated to NASA that.
Oh, it's been longer than that.
Has it been longer than that?
Yeah, it's
They
been
were
like
supposed to know.
15 or 20 years.
Yeah, 2006. So God, that is more than 10 years ago now, isn't it? Anyway, they mandated that. I believe NASA was supposed to know about 75% of the potential dangerous
Okay,
rocks.
so it kind of depends on size. So anything greater than like 100 meters in diameter, we know about 90%. Anything between 150 meters down, we don't have a very good number yet.
Yeah.
We're probably below 50% knowing the next range down.
Mhm.
So we got a lot to do.
Well, I know they approved funding for a space telescope that's supposed to be able to observe these, and there's, I think, a proposal now for one that will look back towards the sun. One of the big unknowns is things coming from inside the orbit of the Earth.
Yeah, we have to send it out to that gravity point, and get a 90-degree angle from the sun, basically, and that way we can see the stuff that's coming in sun side.
Yeah, but it does kind of, the fact that, well, the way this ended up, which is unfortunately kind of common with a lot of things in Congress, is it ended up being an unfunded mandate. They told NASA, you must do this, and we're not giving you any money. And, NASA has a lot of things to spend its money on, which has benefited me from time to time in the past, but I've been one of them. But anyway, so I think the reason why I kind of brought this up is, we try to, do our bit here for the contributing to that, but it never hurts to advocate for these things, to tell the people who are in charge that this is important and we need to do this. So, not to advocate political agitation, but this is an important thing. So I just wanted to kind of throw that out there.
Well, there is and it kind of goes along with these things being unfunded mandates so often. The amount of work that would be necessary and what is required, that doesn't figure into their unfunded mandates or anything else. And it's, once again, it goes back to the saying, nothing's impossible to the man who doesn't have to do it himself.
Mhm.
And so, but then you get somebody like Gary who comes up with a great, fantastic way of doing things, and you blow it all out.
It happened.
Okay. Oh,
Well-
M35.
Yeah, so anyway, we discussed what the focus would be for this week, and Gemini, it's a good February, March constellation. I think we talked about it before once, but it was suggested as a possibility, so we'll focus this month on Gemini. So there's the photograph of the Gemini constellation. I always have to kind of tune my eyes to see them, and one of the things that's always been different for me about Geminis, when I learned the constellations, I learned them from this book called The Stars by H.A. Ray. And probably some of you are shaking your heads or nodding your heads. H.A. Ray was actually, I think, best known as the author of the Curious George books. But anyway, also wrote a book on the stars, which I got a copy of when I was about 10, I guess. And, you know, it was all a book of constellations and the dots connecting them and stories about them and stuff. And he does Gemini differently. And so my image of what it looks like is based on that. And it never quite looks right to me the first time I ever look at it. So as a constellation, it's one of the ones that I always have to kind of adjust my mind to kind of picture which stars are actually in it. But anyway, so Gemini, of course, the twins. In mythology, the twins, we'll talk about here in just a second, but the twins were brothers. As it turns out, they may not actually be twins in the usual sense. One of the characteristics of Gemini, of course, is that it's one of the constellations that lies along the plane of the ecliptic, which is the plane through which the planets move, which means it's one of the zodiacal constellations, and figures prominently in astrology, which I kind of find to be a little, I don't know, mythical, I guess, in and of itself. But it's one of the ones that lies along the plane of the ecliptic. So here's kind of the sort of typical way that it's depicted, connected together. Like I said, in my mind's eye, I always see these connected together slightly differently, because I'm always thinking back to when I learned this from H.A. Ray. So here's some of the stars. Of course, the two principal stars, Castor and Pollux, are the ones that are kind of the heads of the twins, basically. If you want to find them, again, my method for finding things is always find one of the three constellations I really know well, and then connect with dots until it points. And so this one, the pointer, which apparently somebody else has also figured out, is you look at Orion, which is a very easily identified constellation, and you connect the kind of lower left knee, I guess, and the upper right shoulder, which is Betelgeuse, the big red star. You draw a line through those, and it points right at Castor and Pollux. So that's a good way. And then the rest of the constellation is going to kind of spread out this way. So that's my. Apparently somebody else knows this trick too, because I found this online. But that's always been my trick to kind of find Gemini. All right. So what's the story behind Gemini? The mythological story is different than I thought, to be honest with you. I thought I kind of had the broad outlines of the story, but usually when I put these things together, I kind of go back and do a little reading on some of these things. And so the mythological story are two brothers, Castor and Polydeuces, Polydeuces is the Greek version, I believe, and Pollux is the Roman. So Pollux is probably used a little bit more now as the name, but Polydeuces is the one you see a lot in the myths. And they're referred to as the twins, but they actually, at least in most versions of the myth that I saw, had different fathers. They had the same mother. Their mother was Queen Leda, who was the queen of the Spartans, I believe. The father of Castor was the king of Sparta, King Tyndaeus. So he was immortal. His brother Pollux was the son of Zeus. And like we've mentioned a few times here, the family trees and family backgrounds of the Greek gods are pretty messed up in some ways. So you see a lot of kind of carrying on, going on. Well, anyway, So in a way, they're kind of twin sons of different fathers. They're typically depicted in mythology as athletes. Castor was famous as a horseman, was a very skilled equestrian. Pollux was more famous as a boxer and was quite adept with his fists, basically. They, among the other things, they rescued Queen Helen at one point. They also accompanied the Argonauts, Jason and on the ship Argo, which I think they were trying to find the Golden Fleece. Is that right? Which I never really was quite sure what the Golden Fleece actually was. But anyway, they were along on the search for the Golden Fleece. They actually at one point kind of saved the ship from serious damage, windstorm. And Pollux saved the expedition by boxing and defeating a monster. They squared off, and he was able to defeat this monster, so save the expedition. So that's kind of the sort of heart of the story of Castor and Pollux. The other thing that's not such a good, again, there's a lot of really bad behavior that goes on with these mythological features. So Castor and Pollux had two, depending on which version, either cousins or stepbrothers. And most often they're depicted as stepbrothers and also sons of King Tyndareus, who was Castor's father. So they were stepbrothers, essentially. And they were going to marry these two beautiful women, Phoebe and Illyria, at the wedding. And apparently there was a lot of bad blood between the two groups, right? The Castor and Pollux and Idas and Lynceus did not particularly like each other very much. But they were all at the wedding together, and Castor and Pollux decided they became quite taken with Phoebe and Illyria, so they took them. They abducted them. This, of course, did not sit well with Idas and Lynceus. A large fight broke out, and in the course of that fight, Castor, who was mortal, was killed. Of course, Pollux was immortal. He was a son of a god, so he was immortal. And Idas and Lynceus were also killed. Don't know whatever happened to the women. They were probably running away from all this crap, from what I can imagine. But anyway, so this is a frieze right here. This is, I believe, was on one of those things that was on a temple somewhere in Greece, and then I think the British took it, which they had a tendency to do things like that. So it ended up in I think in a museum in London somewhere. But this is a frieze that depicts the abduction of Phoebe and Illyria being taken away, and then of course the men are fighting each other over all this. So anyway, Castor and Pollux were very close they were quite, even though they weren't complete siblings, they were quite close. And so Castor appealed to his father Zeus, who by the way also saved them at one point during the fight by throwing a thunderbolt. Appealed to Zeus to make Pollux immortal, which apparently Zeus was not able to do. There are some limits on what gods could actually do. But what he was able to do was place them both in the sky. So he placed them in the sky in a way that they were visible half the year. Right, so they spend half the year in the heavens and half the year on Earth together still, which is kind of what they wanted. Because they were Argonauts, because they went on the Argos, they've also become sort of important mythological figures to sailors. And there's actually some kind of sailor myth associated with these. If you embark on a voyage in a time when you can see both twins, you're liable to have good luck. If you don't, if only one is visible, and that may seem kind of like an arbitrary myth, but there's actually some climatological there's some climatological support for that, right? Because it moves during times of the year when there's particularly apt to be stormy. So, right, so as both twins become more visible, it's moving into a time of year when it's less likely to be stormy. So I think in some ways this myth got started among sailors for that reason. So that's kind of a little bit of the myth of them. Other traditions had myths associated with the same figures. It's one of the things that when I first kind of started looking at things like this, mainly for curiosity, but also to kind of put together these little presentations, it always struck me that so many different civilizations had similar myths about the same constellation. And I thought, it was, first I thought, oh, it must be just some kind of parallel development, but then it sort of dawned on me, no, they probably are all remnants of even older mythologies that have been passed down, right? And one of them was, of course, from the Babylonians. They saw the great twins in this, two king figures, basically. So these are Ugal-Ira and Neslanta, who were, one translates into the great king, and one translates into something like the wise king, or something like that. So these were the great twins of Babylon, but essentially the same constellation story. Okay, so as far as what you can actually see in Gemini, it's a pretty large constellation, so it kind of encompasses a lot of things. Of course, the major thing is the two stars, Castor and Pollux, or Alpha and Beta Geminorum. There's some look at them there. They're kind of unusual in that usually the Alpha star in a constellation is the brightest, and they go down in brightness as you go up in Greek letter, but it's not the case in the case of Gemini. Beta is actually the brighter of the two stars. It's also the younger of them and the further one away, and so it's this kind of bluish, hotter star here. The other star is actually a kind of an older one, but closer to the Earth, and it is kind of a cooler star, so it tends to look a little redder. Basically, it's about twice the size of the sun, but less than a tenth of the density of it. So less of the density of the mass. So it's a kind of older star, farther along in its development. So there they are, right there. You can see that. This is the constellation right here. There's Orion, and you can kind of use the trick there to see it. As far as other things that you tend to see in here, it's a pretty good constellation for nebulae. One of the kind of more famous ones on here is this thing that falls on this finest NGC objects list. This is actually 2 NGC objects. It used to only be considered 1, but it now is considered 2 separate things, and there's a little bit of a lensing effect going on here. It's like one thing behind another one, right? So the light bends as it goes around. And so you see this rather unusual looking nebula, which is actually now, it used to just be NGC 2371, but now it's split into 2, so it has two separate catalog designations.
Looks like a piece of candy.
It always looks
thinking that same thing.
It always looks to me like a bow tie.
Well, but see, it looks like the kind of candy where you twist it on there.
RASC is Royal Astronomical Society of Canada.
Mm-hmm. It came up with the, what is it, 100 finest objects, I think? Yeah, the NGC is a catalog that, I think, as Gary said, it's a catalog of deep space, mostly deep sky objects, big things like galaxies and nebula and that sort of thing. Okay, so here's some of the other ones. I always like the Eskimo nebula. It's supposed to look a little bit like the face of an Inuit, right? So it's like a face with a big furry hood around it, like a parka. I think the name here is probably a little obsolete now, but you know. The jellyfish, what is IC, by the way? Is it just International Catalog?
No, it's something else, and I can't remember right now, but it's another, I can't get up.
Index.
Index Catalog?
Index catalog.
Okay, good. And so here's the Medusa Nebula, and a Medusa is like a mythical, isn't it the thing that turns you to stone or something like that?
Yeah, the face of Medusa, but it's also, what is it, like a sort of a jelly? It's an animal.
Yeah.
I can't think what you call it.
Anyway, so there's the Medusa Nebula. Also, a lot of really good star clusters in Gemini, and particularly M35. The Messier catalog is another of these object catalogs. The Messier catalog came about because Messier was hunting for comets, and he didn't want to get confused. He was very interested in comets and not much interested in anything else. So he cataloged everything that he thought looked like a comet, so it wouldn't get mistaken for one. So there are the Messier catalog, which has been around a long time now. I think he was doing this probably in the 1800s. So, so a lot of astronomical objects have the M designation, particularly ones that have been either very bright or very prominent or have been known about for quite a long time. So anyway, Messier 35 is actually one of the largest visible star clusters. If you can see the whole thing, it's kind of dim, but if you can see it all, it's actually about the size of the full moon. It's as I said, a relatively dim one. You usually need some binoculars or something.
Yeah, it looks, it's a nice one in binoculars, if you've got them.
And you know, if you've got like a pair of binoculars, they got a nice wide field, so you can see pretty much see the whole thing. But yeah, it's really quite large. And I was really surprised. First time I ever saw it was in a class when I was in college, and I guess I had been kind of, I thought so much about these things as being little tiny things, and it took me a while to sort of adjust my mind to the fact that this thing was relatively large. I had the same experience with M31, the Andromeda galaxy. It's really big, and covers a pretty big patch of the sky. But anyway, so these are some of the star clusters in Gemini. Okay, so that's a quick look at Gemini. Anybody want to add anything? Yeah.
I would just add, because we have a lot of new people here,
Mhm.
so if you are interested in joining NECAL, it's only $35 if you're an individual. Family is $40.
Mm-hmm.
And you can go to our website and pay via PayPal, or you can print out the membership form and mail it to our P.O. box with a check, or I can help you this evening. We're nonprofit,
Painful.
so we have to pay for our operation costs, equipment, insurance for our observatory, which is quite expensive. And so we live off our membership, which the fees have not changed in, what, guys? 22,
Well, not 20, but probably more, 10, 15.
10, 15 years. And donations. So if you're interested in joining, it's a great resource. There are benefits to being a member, even though we do a lot of public outreach, like public nights, and this meeting is open to the public.
Mm-hmm.
Let's see, what else was I going to say? I think that's it.
Yeah.
So if you're interested, please speak up when we get done. Usually there's a little extra time after this meeting if you want to ask more about the club, or if you have a question now before Doug gets to his topic. We're happy to help you.
Yeah. So it's 35 for an individual member,
35 for
40 for a
individual,
family,
40 for family.
15 for a student.
If you are an active student,
Yeah.
taking a class, this could be a college student or of any age, or a private school, homeschool kid. I mean, any of that is $15. And then if anybody joins after, on or after July 1st, which is halfway of the year, all of those numbers, all those fees are half price. But we'd like for you to join early.
Yeah. Yes.
Yep, but if we have an open house and you're not a member, you're very welcome to come out. That's, we still do stuff. Members get things like they get usually one a day. Some of the just information that we get from different websites, and you've got a lot of people here. If you got a question, you can always ask.
Is there anybody here that does not know where Farpoint Observatory is?
Haven't been there, I can find it on the map.
Okay, it's at Mission Valley High School, it's at the Mission Valley Schools.
We were gonna try and come out, I think was it October, November?
It was
Weather came
Yeah.
out.
It was October because we were
That's right, it
going
was October.
to the Great Life
Yeah.
Halloween party.
Yeah, so from southwest Topeka, it's about a half hour to get there. From central Topeka, maybe 45 minutes or so. But we have people come from Kansas City and Lawrence and Manhattan and all of those. We have a large telescope out there. We got a couple of small ones, and then a lot of times members on public nights will bring out some of their own scopes that they like to share with the public. And there's a lot of really smart people in this club, and a lot of them are in this room right now. And so they can help with your equipment, or I'd like to buy something, I want to get into this, and all of that. There's a lot of great great people here.
And thanks Dave for bringing that up, and yeah, we like new members. And any interests, one of the
Yes.
things I think is great about the club is that it has for a relatively small group, it has a very wide range of interests. Yes?
I am curious about your member viewing nights. What is the emphasis of those? What happens?
The idea of a member night, and to tell you the truth, our members do not take advantage of this.
As much as they
But it's an opportunity for our members to either bring out their scopes, or if they have been trained how to use some of our scopes without the public there. Because usually when the public's there, we're busy helping them. But a member night is an opportunity for our members to come together. Now, our membership typically is 30 to 40 people. We have 10 approximately that are highly active. They're the ones that are helping us out, they're using the observatory, they're active people. And the others, we appreciate their support, we try to encourage them. But out at the observatory, we have a 27-inch large scope that we use mostly for near-Earth object asteroid research. And then we have, I have a 16-inch that's out there in one of our smaller buildings, and then there's a club 12-inch scope. Schmidt's Cast, and they're all go-to scopes, and we operate those. And we have
You can see stuff with it.
we have a lot of people with scopes, and it's a nighttime event, so it's hard. It's a hard hobby. It's a hard interest, but it's a great opportunity. The observatory, we're pretty close, and to tell you the truth, in terms of asteroid research, I would say Gary has one at his house. He's in the top 10 in the nation, or in the world, for amateur observatories, and Farpoint's probably in the top 20 on contributions. Our big scope has been down. Through Gary, we put in an improved mirror and a very, very nice camera. And so it was down for almost a year and a half. And because of
improvement,
we paid for stuff, and it just took a long time for it to get to us. So anyway, we're still improving our large scope, and it's a great opportunity to learn things. So I've learned a lot, and I know about this much of what he knows and a few of these other people. So it's a great opportunity.
Obviously, don't know enough to run.
Yeah, the other thing that's nice about member nights, and I remember especially when I was just beginning, you can go out there, there'll be a member there, they're looking at something, you go up and say, what you looking at? And they, and you exchange ideas, and that's how you learn so much stuff.
Yeah.
And, about the sky, about telescopes, binoculars, maps, all these kind of things. It's just in except for a few people, astronomers are usually pretty good about, showing you what they're doing and everything like that. And that's really a neat thing. And I know COVID really kind of put the kibosh on a lot of that, but hopefully we'll get that coming back up again, because I always enjoyed doing that. And we get a coffee pot and refrigerator and microwave.
Necessity room.
Yep.
So
Yes, a necessity.
Our bylaws is if a member is with us at least 6 months and they are active, then we can work with them to give them keys to the observatory and then train them on certain equipment. But we don't pass that out, because we have a lot of expensive stuff out there. So it's an opportunity to have access to some really cool stuff.
Yes. Okay. All right. Well, what we usually do at this point is have a little bit of a presentation. So what I thought I would talk about tonight is probably my favorite thing about astronomy these days, and that's extrasolar planets. So thought I'd give a little bit of a talk about that. And of course, as with many things, it all comes back to Star Trek, right? When I was kid, I watched Star Trek. I was a nerd, don't be surprised.
Yeah.
And when school got out, I think at 3 o'clock, and Star Trek started at 3:30 on Channel 2 in Denver, so I had a half an
Yeah,
hour to get home.
That's true.
And so I actually developed enough, I lived far enough from school and had to run hard enough to get there that I actually became a reasonably good middle distance runner because of the experience of running home to. And I always, my favorite part of the show, of course, was always that beginning when they talk about
Yes,
seeking
yes.
out new worlds.
Yeah.
And of course, I knew even then that there would never be I would never be able to do this in real life or personally. But one of the things I think has been really interesting in astronomy as a field in the last 25 years or so is that 30 years, I guess, is that we're actually beginning to find new worlds around other stars. I think people pretty much always knew they were there, or at least had a pretty good idea where they were there, but the technical problems involved in actually finding them were so extreme that it took quite a long time for it to ever really come to the point where we could actually observe them. And now, not only observing them, but beginning to really say what they are like, understanding them as worlds, not just as something there. So this was, as of the 1st of February, there are 5,307 confirmed exoplanets now. They're being discovered at the rate, I think, of about one every 3 days. So this number will likely be quite a lot larger, not in the very near future. Those 5,000 or so confirmed exoplanets are in 3,900 planetary systems, so quite a few of them have at least 2 and possibly more. There's also 2,504 unconfirmed planets. Now I'm going to circle back to this later, what the significance of that might be. But what that means is that there's been a detection of something that could be an exoplanet, usually in the data stream from one of the observational satellites that are in orbit, which we'll talk about those here in a little bit too, but hasn't been confirmed. And not to kind of skip to the spoiler of the story, but one of the activities that amateur astronomers are engaged in is confirmation of these things. So people with little telescopes like mine can make a pretty significant contribution to astronomy just by confirming the orbital characteristics of exoplanets. So this is, cutting edge science, but it's also cutting edge big science, but it's also accessible to the likes of us as well. As far as the pace at which these things are happening, I know this is kind of a complicated looking graph right here, but what this basically shows is how many planets have been discovered and what types, right? So this is basically the orbit of the exoplanet, and this is its mass over here. And you can see back before the year 2000, there weren't very many, and they all seem to fall into this relatively high mass, which makes sense, right? Because you're going to be able to see big things first. But as time progressed, you can see now we're up here to 2022, there's a lot more of these, and they're available over a much wider range of sizes and masses.
Is that from Kepler started the?
Some of it is from Kepler and from TESS, the kind of Kepler replacement, I guess. But a lot of it is also just dedicated surveys by really big ground-based telescopes. And also it relates to the improvements of technology for finding these things. These colors here represent the way that the planets were actually found. I'm going to talk about what all these mean as we go along here. But the earliest ones were tended to be found by looking at very fine changes in the light that was coming off of them, but now it's becoming easier in some ways to discover them through other means. So I guess the point of all this here is that it's just kind of a goal, a land rush out there, right? We're finding more and more of these things, and more the suggestion is that probably planets around stars are more common than stars with no planets. To the point where this is actually from the National Academy of Sciences. The National Academy of Sciences every 10 years typically does a decennial assessment, a 10-year assessment of what the priorities are in the particular fields. So when the members of the National Academy, who are astronomers and astrophysicists and people involved in this sort of thing, met last time and kind of laid out the vision for what the priorities in the field of astronomy are. A lot of these are things related to exoplanet research. You know, worlds and suns in context. That's all about trying to understand, trying to get information about systems through observation of others. You know, for most of the history of astronomy as a science, we've had in terms of solar systems, we've had an N of 1, right? We've been able to see 1, and so everything we thought we knew about how solar systems worked was based on that one observable solar system, which we happen to be inside of. And one of the biggest surprises in the exoplanet research field is one of the very first exoplanets that were discovered was totally weird. It was big, it was hot, and it was really close to its sun. It was something that was kind of theoretically not expected. So a lot of these things have their roots in exoplanet research. So it's going to, I think, be and continue to be an active area of astronomical science for years to come. You know, people of her age are going to be the ones, I think, that are going to crack the code of how these things actually work and be in this very exciting, this excitement of actually seeing other planets, which I don't know, I'm more or less an Earth scientist, so I tend to focus on our planet, but it absolutely amazes me when I think about what we may discover out there. Anyway, and you've arrived as an exoplanet as a field when you have children's books written about you. So here's a children's book by Deborah Underwood called Exoplanets. Dear Planets, Can We Be Friends? And it's actually pretty interesting. I was able to read about the first 10 pages of it on Amazon, and it looks really interesting. It's about different types of planets and, how we all can form a group. Anyway, so yes, if you have a book about you, a children's book about you. Okay, so among those 5,000 exoplanets, what have we been seeing? And I'm using the kind of royal we here because it's definitely not me doing this stuff. The majority of them are what might be called gas giants, or similar in many ways to planets like Jupiter and Saturn, right? Again, probably not a big surprise because they're the big ones and they're just simply easier to see. The next largest group are Neptune-like planets. Actually, I guess it's the largest group now. These are ones that are somewhere sort of in between, basically. They're kind of icy planets, basically. The super Earths are the kind of about a third of them, I guess. A little bit smaller, somewhere between Earth and Neptune in size. And then finally, the ones that are probably least detectable, and therefore the ones that are known least about, are the terrestrial ones. So these are ones probably similar to Earth. And even though they're relatively small in number, they're a pretty intense field of interest right now because these are the ones that might actually have life on them. They're the ones that are most likely to have life on them. And I'll talk a little bit about how that can be determined as well. So this is, of the 5,000 planets, this is kind of how they break down. As far as the history of exoplanet research goes, it's, as I said, I don't think it's been, the idea that there may be planets around other stars is hardly new. The speculations go back quite a long ways. This is Giordano Bruno, who some of you may have heard of, kind of came to a bad end. Yeah. But he was one of the first people, a first person really to write, speculate about these. And what he basically says is, if fixed stars are centers of systems similar to ours, then there must be, in a sense what he was saying is there must be other planets. And some of his contemporaries, including people like Isaac Newton, were on board with this. It was not considered a crazy idea to think about the fact that there may be planets around other stars. Of course, the problem was that there was simply the observational capabilities just were not well developed enough. There were actually some relatively early claims of discoveries of exoplanets, or at least discoveries of evidence of exoplanets. This was one of the very earliest claims. This is William S. Jacobs, who was a rather famous British astronomer, a member of the Royal Navy. And in the mid-1800s, he made a pretty intensive astrometric study of 70 and Ophiuchi. Never been totally sure on the pronunciation of that guy. But anyway, so what he did was very carefully note its position. And of course, he didn't have photography yet, so he was doing all this visually. And trying to look for very minute changes on the notion that any minute change would be caused by the fact that there may be something, or that this is a position of a star, right? That the path of that star as it traveled through on its proper motion would be altered by the presence of other massive objects around it that would be essentially kind of deviating its path. So this was an early attempt at what's now called astrometric methods, right? Star position measurements. And he claimed to have found some evidence for a planet with a period of about 88 years traveling around 70 Ophiuchi, which, as it turns out, was spurious. There has actually been a planet discovered around this, but couldn't be the one that Jacobs proposed. More recently, Peter Van de Kamp, who taught at Swarthmore College in Pennsylvania, did very similar work, except he had photography, right? So he was able to photograph, and he claimed to have found a planet or evidence of a planet around Barnard's star as early as 1963. He photographed Barnard's star every clear night he possibly could between about 1945 and well up into, I believe, into the 80s. And it turns out again that his data were spurious. Turns out that what he was probably seeing was distortion effects in the lens of his telescope. So he had a relatively large refractor telescope, but it was still a claim that there was a planet around this system. It's actually a really good book about this if you want to put something on your summer reading list, called The Lost Planets. Van de Kamp, I think, stuck to his guns well after it was pretty clear that what he was seeing was really just sort of an artifact of observation. Again, this was an astrometric attempt at this, and the problem here was that the idea of astrometry as a way of detecting planets was fine. They just didn't have the precision in these systems. The photography, the lenses of the cameras, the lenses of the telescopes, they introduced just enough bias that it overwhelmed the potential for astrometric measurements. But now we have much better astrometric tools, right? We have satellites like Parcos that are designed to make very precise astrometric measurements, and some of these have been used to detect some excess. So these were some pretty early claims. So when was the very first confirmed exoplanet? Do we have pop quiz here? And what was it found around? Turns out it was, one more thing. This was not an exoplanet, but this was the first planetary disk that was ever discovered. This is an infrared image, and this was taken from a telescope in Hawaii. And what they did was use an occulting instrument. It kind of blocks out the star, and so you can see. And what this showed was that there's this band of stuff around this, and this would be probably comparable to what you would, if you were looking back at the sun and you would see like the Kuiper belts and the kind of distant objects, right? But this was a pretty strong suggestion that there was matter around this particular star, this Beta Pictoris, so this was a pretty strong hint that if there's this blob of stuff around the star, then probably some of that stuff is coalesced into a planet, right? So this was a pretty important discovery. This was Brad Smith and Richard Terrell. Richard Terrell is still alive. Brad Smith passed away a few years ago. Anyway, back to my question. When was the first planet? Yeah.
I think Gary discovered it, didn't he?
I think it was right after he, after he got off the dinosaur. Well, it turns out that the first actual confirmed detection of an exoplanet was around a pulsar. The pulsar has a really very mouthful name, PSR B1257 plus 12. I have no idea what the name is.
57 minutes plus 12 degrees declination.
And PSR stands for Pulsar Source Radio or something like that?
Something like that, yeah.
So anyway, this is a pulsar. This is an old kind of dead star that is spinning around really rapidly and sending out beams, right? And these two guys, whose names I should know but don't, discovered some planets around this thing. Of course, this is, the planets would be scorched little bits of stuff because these things shoot out just massive amounts of radiation. But this was actually the first confirmed detection. The first one ever found was called poltergeist. The second one was called phobetar, which means something like demon or terror. And the third one was called draguar, which means like dragon or something like that. So these were not given pleasant, friendly sounding names, but these were actually the first confirmed exoplanets. The first one people think about, though, and the reason why we probably went to much more recent, right, was the first detection around a main sequence star.
Yeah.
And this is really when the field of exoplanets research kind of got kicked off. So the first detection around a main sequence star was around 51 Pegasi b. It was by Didier Queloz and Michel Mayor, who subsequently won the Nobel Prize in Physics a couple years ago for this particular discovery. And they found this object that around the first main sequence star, the first sort of sun-like star. And this is, I think, really what got the field started. So there's 51 Pegasi b. It's what's called a hot Jupiter. And again, it was very unexpected, right? Because it was a planet like Jupiter, but bigger, much, much hotter. And that probably contributed to its discovery, because they found this one through very slight changes in the radial velocity of the planet, whether it was moving towards or away from us. And we'll get to that here in just a second. But in order to find this, in order to make it easy enough to find, it had to be a relatively big planet. It had to be relatively close because it had to be pulling its star back and forth pretty rapidly. But it was a big surprise, literally, quite a bit bigger than Jupiter, but also just extremely close to its star, like, measurements of, I think it's less than 100,000 kilometers or something like that. It's just extremely close to its star, which was a big surprise and something that had been unanticipated. So the very first discovery of a sun-like, of a planet around a sun-like star was a really significant discovery in many different ways. So that was the very first one. All right, so why was it so hard to find these things? And again, that may seem like a relatively obvious question, but when you think about it, stars are big and bright and planets are small and dark, right? So if you're trying to find a big, small dark thing that's next to a big bright thing, the observational problem becomes apparent. It'd be like trying to find a grain of dust next to a searchlight or something like that. So it took quite a bit of ingenuity to come up with observational methods for this. So there are 5 ways of finding a planet. And when I designed this, I originally had a link built into this, and apparently it didn't survive my trip here, so I looked this up here. So I figure, why should I do work when NASA has already done it for me? So here's NASA's representation of the 5 ways to find a planet. The original one, and about 1,000 of the ones that have been discovered so far, have been found through the radial velocity method. So if you look at what the radial velocity method is, we talk about objects orbiting each other, right? Or, the Earth orbiting the sun. And the reality is that any 2 things that are in orbit around each other are not orbiting one is not orbiting the other. They're both orbiting around a common center of gravity. Just so happens that with something like the sun and the sun's so much more massive than the Earth that the center of gravity is much closer to the sun. It's actually inside the sun. But the result of that is that as things go around, it'll kind of tug the star a little bit. And if we're looking at it from our perspective, it means it's getting a little closer and a little further and a little closer and a little further, right? And what that means is that the light that's coming from it is being shifted to shorter wavelengths as it comes closer, and stretch to longer wavelengths as it goes further. It's the whole red shift, blue shift thing, except much, much smaller than we're used to seeing it. But if you measure that radial velocity change, that slight shift in the wavelength of light to the shorter or longer, it kind of represents the sort of the wobble that these things in part. So this was the method used for the very first detection. It works really well for particular types of, of planets, particularly big ones that are close. And it works particularly well if the planet is sort of in the line of sight of the star. So I think about 1,000 of them so far that have been discovered so far have been found with radio velocity. Another method, which kind of came along a little bit later and was observationally probably took a little bit more development, is what's called the transit method. But this has become the more dominant method now because it works under a wider variety of circumstances. So basically what the transit method is, if you've got a planet that's passing in front of its star, right, that little tiny planet will dim the light of the star just enough as it passes in front of it that it temporarily looks dim. So if you look at the little graph on the left, see how it goes down and comes back up, right? And so that's called a transit when that happens. And it can be used to not only detect the presence of these things, but also tell you something about the size and the orbital period. And I mentioned earlier that amateurs are making contributions. One of the things that amateur astronomers are doing is measuring this transit. So this works on systems with single planets or with multiple planets. It even works on systems with things like asteroids and things like that. Yeah.
So is this what you're doing then?
I'm not doing this yet, but I'm kind of hoping. So I'm sort of aiming myself in that direction. I'm not making fast progress, but that's this is what I
That's
really
what you will do when you get there.
Yeah,
And that's what amateur astronomers can do.
Yep, yes.
Easiest and best. Okay,
Yeah, this is actually accessible to amateurs.
Okay, thank you.
Direct imaging, this has come about a little bit later. This gets back to the problem of the dust grain and the searchlight, right? You take a picture of this bright thing and it's really hard to see, but there are now some telescopic systems with cameras that are designed to sort of block out the star so you can kind of see the planets, and they're able to directly image these things. So this is a kind of a newer technology. You can kind of see that there. I think the little occulter goes in front here at some point. There it is. You put a blockage in the thing, and then all of a sudden you can see these. And there was a picture published in, I believe, the New York Times about a month ago of some directly imaged planets. So this is another way to find a planet. You can gravitational micro lenses. Gravity will bend the path of light. Right? Kind of think about gravity as being this sort of pucker in space-time, and it kind of bends light when it passes through it. So any massive object will bend the light of things behind it. That's called gravitational lensing. It's used a lot for studying really distant objects. Like I talked a little bit about last month when we talked about distance scales. But you can also use it for discovering planets. It acts in a sense as a type of lens. It magnifies the system, so you can see You can see planets through gravitational lenses. I like this graphic here because it kind of shows the light rays bending, and as you measure them arriving through time, you get an image of that. I love these NASA things because they're way better than anything I can make. And then finally, I think there's one more. Oh yeah, astrometry. Again, this is the method that those original searchers that like Peter Van de Kamp tried to use. Unfortunately, their equipment, they had a sound idea. There was nothing wrong with the concept. It just, their equipment was not up to, didn't have the precision. But now we have much better capability for astrometrically measuring positions of things. And so astrometry has become another way of kind of detecting the presence of exoplanets. So those are the methods that are being used to detect exoplanets. Get back on the slideshow here. And like I said, in terms of the numbers, about 1,000 discovered with radio velocity. The dominant method has become transit searching, because about 4,000 of them, because the major search satellites like the Kepler satellite, which is no longer in operation, and the TESS satellite, which is, and there's another one that's, I think, in the preparation stage right now. They essentially work by looking for transits. They essentially kind of stare at a particular part of the sky and analyze each star to see if there's any by the way, those satellites are also what are producing those unconfirmed observations that are being followed up by amateurs. So here are some of the exoplanet exploration missions and ways that these are being found. I kind of mentioned some of these already. Of course, ground-based observatories were being used. There was an amateur effort, which I'm not sure is still, if it's still in operation, called Transit Search, where a network of volunteer observers were measuring places in the sky or photographing places in the sky and then searching their photographs for evidence of transits. Probably not a lot of this is being done by professional observatories like this, largely because these are very expensive and very much in demand and being used for other stuff. As far as orbital systems go, there were some exoplanet searches done with the Spitzer telescope, which is wasn't necessarily designed for this, but the Kepler one was originally intended for this. Hi, thanks for
Hey,
coming.
thank you very much.
Sure.
Really enjoyed it. She has school tomorrow.
Oh, sure, yeah.
Yeah.
Well, thank you for coming.
We'll be back. Thank you.
Okay.
And so Kepler was the first sort of dedicated planet for observing. And the newer one, more recent one, is this thing called TESS, which is actually a much smaller telescope than Kepler, but it sees a bigger piece of the sky. And it's the TESS stuff that is now being analyzed for follow-up. So if you get involved in this, it's the TESS stuff that is being analyzed. And then this, the Webb has been used a little bit for this, but this WFIRST and New Worlds, those are, the WFIRST is kind of the follow-on for this, so it'll be kind of the next generation planet searcher. All right, so I talked a little bit about types of these things already. Again, the types of these are somewhat, I mean, it's like we see examples of these in our own solar system with one exception. So of course we see gas giants, planets like Saturn or Jupiter. A lot of the gas giants that have been observed are the hot Jupiter types. Those are particularly good for transit analysis because they're relatively big and they go across the planet, the star really fast, right? Because they're close. So if you can, the cadence of observation you need to actually catch a transit it makes it easier to kind of observe these. The one type that is not really present, at least as far as I can tell, in our solar system is this thing called a super Earth, right? It's terrestrial, it's rocky surface, not a gas surface, or an icy surface, but larger than the Earth. Okay, so these are some of the types of exoplanets that have been observed. So the emphasis in a lot of exoplanet work has, for a while there was detection, right? Let's find these things, and that was what things like Kepler and TESS were all about. You know, where can we find these? Can we develop kind of a statistical understanding of the types of stars they're associated with and the types of planets and all that? But some of the more interesting stuff is coming about now by trying to figure out what their physical properties are. And this is the stuff that I find just absolutely astonishing. Using tools like spectroscopy and mostly ground-based telescopes, astronomers are now being able to kind of figure out some of the physical properties of these things. So one of the more active areas in all this is high-resolution spectroscopy of exoplanet atmospheres. So this only works if you have a transiting exoplanet. It has to pass in front of its star, right? So what happens is, if you think about this, right, that little tiny planet with its little envelope of gases around it goes in front of the star. The light from the star passes through that atmosphere and it gets changed. It gets absorbed and spectroscopically altered. And if you think about it, that's observable in nearby planets as well. If you kind of spectroscopically analyze the atmosphere of the Earth, you'd see something like this, right? You'd see this absorption features here that are water molecules, right? The water molecule absorbs light at these very discrete wavelengths. Ozone absorbs at these very discrete wavelengths. It's present in the Earth's atmosphere and the stratosphere. So that would be another, you could analyze the presence of that. Carbon dioxide in the atmosphere. All of these, this pattern of kind of lines and squiggles in the spectroscope is like a chemical signature of the presence of these particular molecules. So here's what, the blue Neptune, there we go. A lot of methane here in Jupiter, a lot of, Saturn, a lot of ammonia and acetylene. One of the things to notice here, though, is look at the difference between these, right? This is a really pretty simple spectrum, right? The absorption lines in here are not that complicated looking, and they're associated with, mostly with, 5 molecules composed of 5 things. This one's even simpler. Look at this. It's weird and all over the place, right? What's the difference? One of these things is not like the other one. And what's different? Water. Water, but even more fundamental than that. What's on Earth that is not on either of these two guys? Life. Right. So that actually kind of points to the composition of the Earth's atmosphere is fundamentally a result of the fact that it has an active biosphere. Right? If you took all the gases in the Earth's atmosphere, mixed them together in a jar and let it sit there, they would react down to something very different. The reason why it stays out of equilibrium, the reason why the chemical composition remains the way it does, is the biosphere makes it there. And that becomes the basis for looking for life elsewhere. So I think, when life gets discovered, which I think will happen in my lifetime, and I'm hoping it will certainly happen in the young lady that was here, her lifetime, it likely won't be, a signal from the stars or anything like that. It'll be a chemical signature that indicates that there's an active biosphere on one of these. And it'll be something like this. So here's kind of how the whole idea works, right? And it takes a really just extremely precise and extremely sensitive to instruments connected to really big telescopes to actually do this. But the idea is, right, that light passes through the atmosphere, right? Just gets spread out in the spectrum, and the resulting signal, this is the star alone, this is the star plus the atmosphere, and you basically digitally subtract this from that, and whatever's left over is the evidence of what's going on in the atmosphere of the planet, and that's really an active area in this. I, from time to time, when I have a little spare time, read some papers about this, and I gotta admit, I don't really understand the nuances of them all that well, but it's really impressive the speed at which this is progressing. So here's some examples, right? This is an exoplanet called WASP-19b, and they found methane in its atmosphere, right? Hydrocarbons, and also hydrogen cyanide. And again, these are not necessarily biomarkers in and of themselves, but they are kind of suggestive of chemical processes that could be sort of life-related. So this is in no way a signature of, a confirmed signature of life, but it is really suggestive. And here's what other biosignatures, this would be the biosignature of Earth, basically. If you were observing the Earth from elsewhere, you would see something like this. This is wavelengths down here. So we're getting out into the infrared part of the spectrum, right? Why is that important? What else is observing in the infrared part of the spectrum these days?
The Webb.
The Webb, right? So one of the missions of the Webb telescope is to do this sort of work, and it's optimized to see in the kind of thermal infrared part of the spectrum, which was largely done because one of the missions of the Webb was to see deeply redshifted things, right? Things that have shifted out to very long wavelengths. But it also turns out to be really good for looking for biosignatures. So,
Did
again,
anybody happen to watch the PBS show last night about the James Webb?
ooh, I didn't know it was.
There were 2 people who were looking at a particular planet, and they were using 2 different methodologies to try to determine, and they were looking for
biosignatures.
Atmospheres.
Mm-hmm.
And one method said no, and the other method said maybe, because they think it found carbon dioxide.
Mm-hmm.
And so they were doing it 2 different ways, partly because they didn't know which way was going to work best. But they've been able to already, with the James Webb, they're working on atmospheres.
I think I heard about I didn't see the show, but I think I heard about some of that work.
Yeah.
Yeah.
Yeah, and of course, at James Webb, they've got, they found the most distant galaxy so far, and they said, right now, this is the most distant, I don't remember how far it was, but they said, at the rate we're going, we'll find it further than that. I mean,
Yeah.
they get very close to the Big Bang. But I didn't realize that they were already looking at atmospheres
Yeah,
with the
oh,
James
yeah,
Webb,
yeah,
and
yeah.
that was just really cool.
Yeah, it's pretty impressive stuff.
Mhm.
And again, I'm reasonably confident that there'll be a fairly clear biosignature of some type before too long.
Yeah,
Which would be
somebody
really
will have to
exciting.
go up and try to sell them something.
That does actually kind of bring up a question, if you find life on another planet, of course, we're not in any position to bother them, we can barely get off our own planet, but it does kind of bring up an interesting question. But anyway, so biosignatures is a major kind of area of interest right now. All right, so again, I kind of mentioned this earlier, but I want to kind of wrap this up by circling back to it. What can you do as a hobbyist or a volunteer observer? And it turns out in the case of exoplanet observing, quite a bit. There is a network of people that is involved in this. This book right here is called Exoplanet Observing for Amateurs. This guy that wrote it, Bruce Gary, is an interesting character. I read through his website one night when I had nothing to do, and he's a really interesting guy. He was a radio astronomer that retired, and his hobby now is exoplanet observation. He's also probably just a world-class crank, but a really interesting and smart one. But anyway, he wrote this book, which you can buy a physical copy of it, but you can also download it on a PDF, and it tells you like everything you need to know to basically do exoplanet observations. And it doesn't require especially elaborate equipment either. This is not Bruce Gary's telescope. He's got a couple of, he lives somewhere in southern Arizona, and he's got his backyard observatory. This actually belongs to another observer who's more associated with AAVSO. But anyway, but yeah, you can kind of see that this is, this is not nothing, but this is also not exactly an elaborate system, and yet it can be used to do some pretty noteworthy follow-ups on these. So as far as getting involved in all this goes, there are several organizations. Probably the one that's doing a lot of this is the American Association of Variable Star Observers, who now has an exoplanet section, and you can report data through this. They actually offer a course which I took. Unfortunately, this was supposed to be in front of that. The AAVSO offers courses to members and non-members. A little bit of a cost associated with them, but they're usually pretty good. And they had one on exoplanet stuff where they actually take you through the process of how to do follow-up measurements, teach you how to use a software package. And so if you're kind of interested in getting into it and you've got your own equipment, this is one of the avenues that you can go along for. The lead observer on all this is a guy named Dennis Conti, and I taught this course that I took. If you don't have telescopes or your own facilities, you can still get involved. This was a NASA program called Exoplanet Watch. It's now completed, but it was basically a citizen science thing. You basically got a piece of data from one of the satellites, usually from the Kepler satellite, and did some analysis on your own computer, and of course they kind of walked you through how to do all that. So this was a way to kind of harness the interest of people who had computers and time, but maybe not telescopes. This is another kind of similar thing. This is Exoplanet Explorers. I had a link built to this, but unfortunately something happened to it. But this is a kind of a similar thing, and this is taking data from the TESS system. I did a presentation, I don't know, it's been a little while now, about the TESS, using TESS data and doing a little bit of exoplanet analysis on it. And I still have that code if anybody's interested and wants to kind of get involved in some of this. So this is another avenue that you can get involved with. Okay, so that's it. Again, I think this is, in my opinion, one of the more exciting areas of a already pretty exciting field. I am hoping one of these days when time is finally a little bit easier to come by, of doing some of these kinds of things. If anybody's interested, wants to kind of team up on that, I would be delighted to do so. But that's it. Any questions?
Cool.
All exoplanets discovered are in our galaxy right now, right?
Far as I know.
Because I think a lot of people, when they say, okay, you're out in the heavens looking for exoplanets, I think it's easy to think, oh, it's all galaxies.
Yeah,
But they're the ones in our galaxy.
I think it would be
Because you
pretty,
can see other galaxies, so I think it's complicated for the layperson to think pretty much everything I'm seeing is in our Milky Way galaxy.
yeah.
So,
I think it would be pretty technically hard to see an exoplanet. You'd have to be able to actually see a star in another
I wonder if the
galaxy.
Andromeda galaxy, it's pretty big.
Yeah, and you can see some individual stars, I think. Can't you?
So, it was nice, thank you.
Very, very interesting. Thanks,
Okay.
very cool.
So again, standard plea, if anybody wants to give a presentation, I would be happy to yield the floor.